In this lecture, we present the Cauchy Riemann equations and show a standard derivation of the Cauchy Riemann equations. Let z be equal to x plus I times y, where x and y are real numbers. Let f of z be equal to u of xy plus I times v of xy, where both u and v are real valued functions. If f is differentiable at z, or that f prime at z exists, then u sub x, or the partial derivative of u with respect to x, equals v sub y, which is the partial derivative of v with respect to y, and the partial derivative u sub y equals minus the partial derivative v sub x. All these partial derivatives are evaluated at z. These two equations together are called the Cauchy Riemann equations. Satisfying the Cauchy Riemann equations is a necessary condition for differentiability at z, but it does not guarantee the existence of f prime at z. A standard proof of the Cauchy Riemann equations for the existence of f prime uses the definition of the derivative and the existence of limits at a point. We find f prime of z using the difference quotient f of z plus delta z minus f of z all over delta z. If f prime of z were to exist, then the limit of the difference quotient should always be equal to one value. This is regardless of the path we follow towards z, as delta z tends to 0. But we will use simple paths towards z. Path number 1 is along the horizontal line where every complex number has the same imaginary part as z, and the imaginary part of z equals y. Therefore, along this path, delta z equals delta x, where delta x is some real number, and z plus delta z equals x plus delta x plus I times y. So the difference quotient becomes u of x plus delta xy plus I times v of x plus delta xy minus f of z, which is equal to these terms, all over delta z, which is also delta x. We take both u terms and put them together in one fraction. We take both v terms and put them in a separate term. The first fraction is the difference quotient for the partial derivative of u with respect to x. The second fraction is this time the difference quotient for the partial derivative of v with respect to x. Therefore, assuming u sub x and v sub x exist, the difference quotient tends to this quantity as delta z tends to 0 along path number 1. And if f prime of z does exist, this is the formula for f prime of z along path number 1. Path number 2 is the vertical line through z, where every complex number has the same real part as z, so that delta z equals I times delta y. Delta y is some real number, and z plus delta z equals x plus I times the quantity y plus delta y. This is what we get for the difference quotient along this path. We put the u terms again in one term, and we do the same for the v terms. 1 over I in the first fraction equals minus I in the second term cancels out. This part of the first term is the difference quotient for the partial derivative of u with respect to y. The second fraction is the difference quotient for the partial derivative of v with respect to y. And assuming u sub y and v sub y exist, the difference quotient tends to this quantity as delta z tends to 0 along path number 2. This is also the formula for f prime of z that we get along path number 2. So if f prime of z were to exist, these two formulas should be equal. Recall that if two complex numbers are equal, their real parts should be equal, so that u sub x equals v sub y. Their imaginary parts should be equal as well, so that minus u sub y equals v sub x, or that u sub y equals minus v sub x. And so we have the Cauchy Riemann equations. We now present 3 examples related to the use of the Cauchy Riemann equations. For the first example, we verify the Cauchy Riemann equations for f of z equal to 1 over z or 1 over x plus I times y. 1 over x plus I times y equals x over the quantity x squared plus y squared plus I times minus y over the quantity x squared plus y squared, so that u equals this part and v equals this part. We leave the differentiation as an exercise for the viewer, but these are what we should get for partial derivatives. U sub x equals this fraction, v sub y equals this fraction, u sub y equals this fraction, and v sub x equals this fraction. We see that u sub x and v sub y are equal, and that u sub y equals minus v sub x, so that f satisfies the Cauchy Riemann equations. If we were to use this formula for f prime of z, we would have u sub x plus I times v sub x. If one were to square 1 over z and take its negative, one could verify that this formula for f prime of z would also be equal to minus 1 over z squared, which would be just as what we'd get had f been a function of a single real variable, just as in introductory calculus. For example 2, we verify the Cauchy Riemann equations for f of z equal to e raised to the power z. E to the z power equals e raised to the power x plus I times y, which is equal to e to the x power times e to the power I times y. By Euler's formula, e to the power I times y equals cosine y plus I times sine y. Therefore, f of z equals e to the x power times cosine y plus I times e to the x power times sine y, so that u equals e to the x power times cosine y, and v equals e to the x power times sine y. One can verify that these are the partial derivatives that we should get. U sub x equals v sub y, and u sub y equals minus v sub x, so that f satisfies the Cauchy Riemann equations. Once again, using this formula for f prime of z, u sub x equals e to the x power times cosine y, and v sub x equals e to the x power times sine y, so that f prime of z equals e to the x power times cosine y plus I times e to the x power times sine y, which happens to be e raised to the z power, so that the derivative of the exponential function on the complex plane is itself. For the third example, let f of z be equal to x squared plus y squared plus I times 2xy. We determine where we can be sure that f is not differentiable. U equals this part, and v equals this part. These are the partial derivatives of u and v that we should get. U sub x equals v sub y, but this time u sub y equals minus v sub x only if 2y equals minus 2y. And that means y has to be 0. Therefore, f does not satisfy the Cauchy Riemann equations if y is not equal to 0. Y equals 0 corresponds to the real axis, so that f prime of z does not exist if z is not on the real axis or if z is not a real number. So what if z is real when the Cauchy Riemann equations are satisfied? Does f prime exist for real numbers? And if not, what other condition or conditions do we need to guarantee that f prime exists for real numbers? Here's a theorem to help answer this question. We state the theorem without proof. If, in addition to satisfying the Cauchy Riemann equations, u and v have continuous partial derivatives at z, then f prime at z exists. Each of these derivatives of u and v is continuous everywhere. It should be no surprise, since both u and v are polynomials, and polynomials have continuous partial derivatives everywhere. Since the Cauchy Riemann equations hold only for real numbers, f prime of z exists only when z is a real number.